So I'd like to continue what we started in part 1 of this video before my camera battery died. If you recall, we were taking the limit as n approaches infinity and using our summation formulas to evaluate this integral here using Riemann sums. And as we're taking the limit as n approaches infinity, our subintervals just become increasingly smaller and smaller until the approximation that we come up with is exactly equal to the integral. And I like to use Riemann sums for this purpose. We had gotten all the way to this step here, where our n terms are just starting to cancel out. So here we have an n squared term over an n squared term. Well, that just goes to 1. Here we have 2n over n squared. One of the n's is going to cancel out, leaving you with an n in the denominator, but that's still going to go to 0 as n approaches infinity. And similarly, our 1 over n squared here is also going to go to 0. Here you have a 2n squared over n squared, that's just going to equal 2. Here you have a 3n over n squared, that's going to equal 3 over n, which is going to go to 0. And then this 1 over n squared is going to go to 0. Here you have an n over n, that's just going to equal 1. Here you have a 1 over n, which is going to go to 0, again, as n approaches infinity. And then minus 35 over here at the very edge of our paper. So we're going to evaluate this. We're ready to get rid of our n terms now, because they've either all gone to 1 or some constant or 0. So here in this first term we have 625 over 4. 625 over 4. And that's going to equal 156 point and 1/4, which is 0.25. And then we have negative 125 times 2 here, which is going to give us minus 250. Here we have a positive 150 times 1. And then we have our minus 35 here. So here we said 156.25 is what this equals. And I'm just going to combine our positive terms here. So we have this positive term and this positive term. And when we add 156.25 to 150, we get 306. And we just drop down our 0.25 here. If at any point you want to just stop the video and just double check the algebra or the arithmetic, or just work through it yourself, I encourage you to do so. You'll learn more that way if you go through all the steps yourself and not just take my word for stuff. Here we have, this is a negative term, this is a negative term. We're going to combine these into one negative term. That's going to give us minus 285. And we are just one step shy of our answer here. If we subtract 285 from 306.25, that gives us 21, and we just carry our 0.25 here. And that's our answer. So we went through this long evaluation here as the limit as n approaches infinity of our right Riemann sum, and we could have used left Riemann sums or midpoints here. I just find that right Riemann sums are simpler and easier to use for this purpose. And we used our summation formulas. We got all the way down to this point. And as the limit of n approaches infinity, our subintervals are going to get smaller and smaller. So this is the exact area underneath the curve, x cubed plus 1. And just to give you an appreciation of what we've accomplished here, let's use integration to evaluate the integral. And you're going to see that it's actually faster and simpler if we just use our power rule from integration. Alright, so now we're just going to evaluate the integral as we normally would. We have our integral from -2 to 3 of x cubed plus 1. That's going to be dx. And this is easy to evaluate. We've done this a bunch of times before. This is just going to equal x to the 4th power over 4 plus x evaluated at -2 and 3. So when we have 3 to the 4th power, that's going to be the same as 9 times 9, which is 81 over 4, plus x at 3 just equals 3, minus, I'll put it in brackets here, so we have -2 to the 4th power divided by 4. That's just going to equal 4. And then we have x at -2 is just a -2. So here we're going to have a -4 and then a -2, so that's going to equal a +2. And this gives us 81/4 plus 3 minus 4 plus 2 is going to give us a +1. And when we do the algebra here, this is going to give us 85/4, which is equal to 21.25, which is the exact same answer. The exact same answer that we got up here. There was just fewer steps involved to get there. Now, just to give you a broader appreciation of what we've done here, this is the curve that we were looking at. This is x cubed plus 1 on the interval from -2 to 3. And this particular chart of rectangles here is when we were using midpoints, if you recall. But now we found the exact area underneath the curve. So that would be this area right under here, all the way up to there, minus this area there, all the way down to there, below the x-axis. And we've shown that that equals exactly 21.25. That would be 21.25 some units squared. And we have, over the course of the last few videos, we have solved this in multiple ways. First, we took our left Riemann sum, and we showed that the value of the integral must be greater than 5, because we figured that 5 would be under the greatest underestimate that we could have. We also, this is a little bit out of order here, but we did right Riemann sum, and we showed that the integral must be less than 40. So then we had a lower bound and an upper bound that it must be equal. We knew that the value of the integral, it would be greater than 5 but less than 40. Now, if you just took the average of your left and right Riemann sums, that would give you 22.5, which is somewhere in the middle. We did our midpoint rule, however, and we approximated our integral at 20.625. And this is considered closer to the actual value than this, because sometimes when you take a left or right Riemann sum, well, you can have a significant underestimate or a significant overestimate, and sometimes the underestimate could be more significant than the overestimate, just depending on the nature of the curve. So when we did our midpoint calculation here, we got an approximation that was closer than this 22.5 here. And if you look at the actual answer here, this is the answer that we get when we use the limit as n approaches infinity of our Riemann sum process here, or we could just use integration to get the exact same answer. And we figured out that the integral equals 21.25. This is the actual area under the curve. And when you notice that the midpoint rule is 20.6, well, that's almost, if you just round up here, that's almost 21. So I hope that these past few videos have just given you a greater appreciation of this whole process and where some of these ideas of integration come from.